Hello, and a very warm welcome to you all on this course on polymer processing at the University of Wisconsin-Madison. My name's Bart.
I'm Heidi.
And I'm Marius.
Together, we're going to be your course instructors.
This course is going to be taught in two parts, with Bart taking the first half of the course and Marius and I sharing the second half.
So what we'd like to do is, in this introductory session, is to first of all give an overview of the course and its contents, and then to give some information on its assessment.
Once this has been done, I'd then like to spend a little time to set the scene as to why polymer processing is important. I'll do this by giving a brief history of the discipline and then highlight a few of the major challenges that are faced today that need to be overcome.
We'd like to start with some of the key learning outcomes from this course. Number one, at the end of this course, you'll be able to state the differences between the various polymer processing techniques used to convert polymers to useful products. Number two, apply the concepts of transport phenomena to the design of polymer processing operations. Number three, at the end of this course, you should be able to describe the connection between polymer molecular structure and polymer flow by using the basic concepts in polymer rheology. Number four, you should be able to analyze the connection between the properties of the product and its processing conditions. Number five, you should be able to theorize as to the requirements for the design of recycling schemes for various polymers. And number six, at the end of this course, you should be able to compare what is possible via traditional processing methods versus modern methods like 3D printing.
The main book we'll be using for this course is the Polymer Processing Principles and Design by Donald Baird and Dimitris Kolias. The optional textbook we are going to be using is Polymer Processing Principles and Modeling by Agasan et al. And it's actually over here, you can actually see the original French version, which is also very interesting.
So I'd like to give a little bit of an overview now about the course structure. Now, the course structure is going to be divided into two, as Marius and Heidi have already said, and I'm going to be taking the course up until the midterm. So I'd like to detail the contents of the first 7 lessons that I'll be giving, and it starts with the one we're doing today. It's the introduction. So it's all about the motivation for the course, and I'll be going on to explain a little bit about polymer processing operations in very broad overview. I'd also like to have an illustration on this of how processing and polymer nanostructure are intimately and intrinsically intertwined with one another. So processing and polymer are both very, very important to determine the final product properties. The second lesson, I'm going to be doing a revision of isothermal Newtonian flow and including things such as lubrication approximation and looking at velocity profiles in non-circular ducts and some methods to evaluate frictional losses in pipework. The third lesson will develop on this. I'm going to talk about isothermal generalized Newtonian fluids, again using the Cauchy momentum equation as the most fundamental principle, and I'm going to show you how to solve the resulting equations both analytically and numerically using Mathematica. The fourth section of the course goes and looks at viscoelasticity and its effect on polymer processes. So I'm going to motivate and introduce this and then give a brief revision on the field of rheometry. I'll also be talking a little bit about the effect of molecular weight and the effect of temperature on material properties. And rheology spills over into the fifth lecture as well, where I'll be talking about constitutive models. And I'd like to introduce and remind you of some nonlinear convective constitutive models, such as Oldroyd 4 constant, Giesecke's, White-Metzner, and really focus on how we fit these to experimental rheometry data. I'll give you a little bit of an overview of why we might want to do this and the value that gives us, and also a bit of an overview on how viscoelastic flow modelling can be done. The sixth lesson will be the start of 2 lessons on thermal analysis, and so I'll be introducing the vector form of the energy transport equation. I'll be looking at some non-dimensional groups that can help us understand the problem that we're solving, and then I'll solve the energy equation in the 6th lesson for convection, for conduction, and for radiation. Predominantly, this will be done analytically, but some of the radiation calculations will be done numerically. In the 7th and final lesson that I'll teach, I'm going to evolve what we're doing with energy transport a little more, and I'm going to look at two-dimensional problems, non-steady state problems, and introduce you to things such as Heisler charts and concepts such as viscous dissipation. Again, a lot of this is going to be done numerically, and so there'll be some mathematical code associated with this as well.
For the second part of the course, myself and Heidi will take over. Part 8 of the course will be about mixing in polymer processing. We'll give you motivation, concepts and mechanisms, characterization and measurement, dispersive and distributed mixing, thermodynamics, and chaotic mixing. Following that, part 9 will look at extrusion, forming, and design. With that, we'll look at viscoelastic phenomena in that as well. We'll look into extrusion instabilities, sheet and film dies, annular dies, profile extrusion, and multi-layer structures. In week 10, or part 10 of the course, we'll again talk about extrusion from application and types of extruders, single screw extrusion design and operation, twin screw extrusion design and operation, and mixing and experimental design for these operations.
After that, we'll pick up with post-die operations, which includes fiber spinning, film casting, and film blowing. And then we'll transition to molding and forming operations like injection molding, compression molding, thermoforming, blow molding, calendaring, additive manufacturing, and 3D printing. Then Marius will have a unit on sustainability, including bio-derived, renewable, and biodegradable polymers. We'll talk some about life cycle analysis, recycling of polymers and upcycling of polymers, properties of green polymers, and energy considerations associated with recycling. Then we'll finish up in week 14 with a unit about mass transfer and reactions in polymer processing, mass transport in polymers, diffusion, solubility, permeability, mass transfer coefficients, devolatilization, and reactive extrusion.
Brilliant. Thank you very much, Heidi and Marius. So what I'd like to talk about now is assessment. I'm afraid we do have to do some assessment on this course. It's everybody's favourite thing. So assessment's effectively going to take part of two different things. Per each course section, there's going to be between 4 and 5 homeworks, and these will be issued on certain weeks of the course. So it will give us 9 or 10 homeworks in total. And each homework will effectively cover material that's been covered in the most recent lessons. We'll also be doing an assessment on the first part of the course around the midterm. It's not going to be a formal midterm exam. It's going to be more a sort of a miniature project. And there'll be also a final assessment which will focus on the second section of the course. And so hopefully that will give a good weighted balance of ability to be able to perform in each of these sections. So in terms of grading, on the board there, I've put the list of letter grades and their corresponding percentages. And the minimum required to pass the course is a C. I think that will involve a resit, but if we go for a B, C or a B, then you're on safe ground. So hopefully those will be useful data for you as and when you progress through the course. Really, the key message I'd like to get across with this is that we hope you enjoy this course. We really hope you find it interesting, that you can find it relevant and important to whatever your current career is and to your future career as well. So what I'd like to say now is to say a big thank you to Heidi and to Marius. I'm looking very much forward to seeing you both again soon in the second part of the course.
Sure, we are too. Bye for now then.
Yep, thank you. And we'll see you soon, and bye for now.
Thank you very much, both of you. So what I'd like to do now is to take a look at how the polymer processing industry started. To do this, I need to move from this beautiful setting in Scotland and head to the equally beautiful tropical rainforests of Indonesia to try and find an absolutely remarkable natural biopolymer. So here we are in the indigenous Indonesian forest, and the reason why I'm here is because a relative of the rubber tree. That particular tree is called Gutta-percha, which produces a thermoplastic latex-based product of the same name. So you may be familiar with latex, natural rubber, And if we think about that to start with, latex has been collected for a number of hundred years now and comes from the bark or incisions in the bark of the latex tree. Now, chemically, latex is a polyisoprene. It's actually a cis polyisoprene, as I've shown there on the whiteboard, and it is a liquid product that is collected and then processed into a solid set product. Now, gutta-percha is in many ways quite similar, yet radically different. And let me explain why I say that. So firstly, one of the radical differences is the gutta-percha tree, which is a distant relative of the latex rubber tree, is all about leaves. And so the polymer that's of interest is collected from the crushed leaf and sometimes the crushed fruit. The similarity comes into play when you think about it chemically, because gutta-percha, the polymer, is also a polyisoprene. It's actually the trans isomer of polyisoprene. So it really is a case of cis polyisoprene, latex rubber, or trans polyisoprene, gutta-percha, that gives a remarkable difference. And that remarkable difference is that gutta-percha, once it's been collected, and that's by means of processing and crushing the leaves and then extracting the polymeric product from those crushed leaves, and then taking that polymeric product through a number of purification stages until you end up with basically a set block of trans polyisoprene. Now, that set block of trans polyisoprene will effectively soften at around 60 degrees C, and so it's thermoplastic. And so gutta-percha represents, in effect, the world's first engineering thermoplastic. Now, the indigenous peoples of Indonesia knew of gutta-percha's properties going back millennia, and there's accounts of how maybe tribal knives were covered in gutta-percha as a handle to soften it for use, or how other tools and other artifacts were made of this quite remarkable biopolymer. And there's a first account in the Western world of gutta-percha is around the 1650s, but it wasn't really until the 1850s that it was really appreciated and used on a massive industrial scale. So that ductility and that formability allowed many, many innovations from about 1840 or 1850 onwards. One of the machines that was invented to process gutta-percha was the screw extruder. And there on the whiteboard is a representative image of one of the first screw extruders that were used for making gutta-percha pipes. And that again dates from around 1850 or so. It wasn't just piping that was used and produced from gutta-percha. It was a whole variety of things that we would associate today with polymeric products or plastic products. For example, the first golf balls, or an innovation in golf ball technology, came about through coating the ball in gutta-percha to give it the right mechanical properties to play golf with. Furthermore, gutta-percha was in effect injection moulded to make bottles, much as we do today with, for example, low-density polyethylene. And the properties of gutta-percha were such that it was effectively inert to lots and lots of different chemical environments. And so the example there I've put on the whiteboard is a bottle for hydrogen fluoride, or hydrofluoric acid, made from gutta-percha. And it's the sort of thing that we'd associate today with maybe a low-density or a high-density polyethylene. One of the major uses as well for gutta-percha was biomedical, and it was used a lot in dentistry, and the first dentures and implants were effectively made from or utilised in their manufacture gutta-percha. It's interesting that today one of the remaining uses of gutta-percha is in root canal fillings, and a good friend of mine has just had a root canal filling made from gutta-percha. So gutta-percha was revolutionary in many senses. Revolutionary in the West, already known about in the indigenous areas from whence it came. And it allowed a whole range of different consumer products to be made in ways that just weren't possible before. One of the major innovations that came around with gutta-percha was recognizing its use in the construction of other products. And again, when we look at the sorts of products I'm about to talk about, it's the products that we would associate today with synthetic polymers. One of the things that gutta-percha allowed was the construction of cabling, electrical cabling. In this case, it was telegraph cabling. So the first transoceanic telegraph cables, telegraph being the forerunner to telephone, were constructed using gutta-percha as the insulator between the electrical conductors. And so the diagram I've put there on the board is of a cable-based outer, much as you'd get a sort of a structural cable. In the middle of that cable-based outer, you've filled it with gutta-percha. And then you've got your individual conducting strands, of which there are 4 in this particular picture, each of which are cables covered in insulator, the insulator being gutta-percha. And the way insulated cables were manufactured then, and we're talking back half of the 1800s, would be very similar to the kinds of wire coating dyes that we would expect today, with perhaps PVC as the insulating material. And so there on the board, I've put 2 pictures, the first of which is a wire coating dye, where you've got your copper conductor effectively being dragged through, under tension, an area of material, in this case gutta-percha, that will coat it. And so it's a sort of a pultrusion type wire coating. And beneath that, I've put a diagram of the apparatus that one might use. And so you've got your coil of wire feeding into your wire coating dye, feeding into a cooling bath, feeding then into downstream processing machinery, typically spooling and pulling. And this looks very, very reminiscent of some of the modern wire coating operations that we see even today. So gutta-percha was a major discovery in the 1840s and 1850s. It spurred many new materials, it spurred many new technologies, and those materials and technologies are very much the sorts of materials and technologies that we would today associate with a whole variety of different synthetic polymers. So gutta-percha fell out of fashion in around sort of the early 1920s, 1930s, when synthetic polymers were pioneered. And the 1930s were a hotbed of polymer chemistry and polymer technology. On both sides of the Atlantic, there was a lot of ongoing research. If we focus in the European area, in Great Britain, there was the chemical company Imperial Chemical Industries, or ICI. And in 1933, 2 young chemists from Oxford, Reginald Gibson and Eric Fawcett, were employed in one of the major research laboratories in Winnington. And they were employed because they were not only brilliant chemists, but they were young and strong. And in those days, the experimental apparatus for synthesizing what were termed high polymers were incredibly high-pressure devices. And so you needed young, fit, strong people to operate them. So the total reactor that we're talking about was pressurized manually by means of a screw that was manually turned around and screwed into compressed gases to around 500 or 600 atmospheres. And there's a wonderful account in the original laboratory books from Fawcett and Gibson that describes the sort of experiment they were doing. They noted down that the gases were introduced into this reactor, which was nicknamed the bomb. It was brought up to pressure, and it was left overnight, and there was a pressure gauge on the reactor. And when they came back into the laboratories the next morning, the pressure had fallen to 0. And they were quite crestfallen by this, because this suggested that there'd been a leak of some sort, and that the effort that they'd gone to prepare the reactor and to undergo the research had basically fallen to nothing. So they opened the reactor up and were very surprised to discover, and I quote, "a waxy solid in the reaction tube." That waxy solid was the world's first ever low-density polyethylene. And I've drawn the structure of polyethylene there on the board for you. A very simple molecule, but actually one with great controversy, because in that era, in the early 1930s, it was thought that it was impossible to synthesize a high polymer made of ethylene. In fact, Hermann Staudinger, one of the great German chemists, was very much in opposition to the fact that these molecules could be synthesized. And there's a wonderful story of a conference in 1934 where Fawcett and Gibson and Staudinger were at a conference in Cambridge, directly presenting one after the other, one saying, "Hey, look, we've made polyethylene," and the other saying, "You can't do this." So there's always a very interesting story that surrounds these types of technologies. The other controversy surrounding polyethylene at the time was that it couldn't be repeated. The very next experiment, the reactor went wrong. Being at 1,000 bar or thereabouts with compressed gases, it detonated and it razed the laboratory to the ground. Due to the controversy with Staudinger, experiments weren't repeated for probably about a year or 2. Fawcett and Gibson were redeployed elsewhere, but the experiments eventually were redone. Polyethylene was successfully synthesized, and then the whole thing was put under a top secret embargo. And actually, polyethylene was the first dielectric used in airborne radar, which was pivotal to the success of the Battle of Atlantic during the Second World War. On the other side of the Atlantic in the 1930s, there was a brilliant chemist, Wallace Hume Carruthers. Now, Wallace Hume Carruthers was a lecturer at Harvard University and also a research fellow at DuPont and de Nemours, and he was responsible for the discovery of a number of high polymers. It was condensation polymerization in particular that he was looking at, so polyesters and nylon. 6,6 nylon, the structure which I put there on the board, was one of Carruthers' brainchilds. Now, Carruthers was a very interesting and somewhat tragic figure in his own right, and he was a manic depressive, and he was alleged to have always carried around a little bottle of cyanide with him. Unfortunately, in the mid-1930s, he used this cyanide to devastating effect and committed suicide, and so he never got to see the commercial success and the industrial success that his inventions brought. He died long before the advent of the nylon stocking, which was a global phenomenon at that point in time. And that's really a very, very sad story indeed. So from the mid-1930s onwards, there was a lot of discovery in terms of polymer science, of polymer chemistry, and of polymer synthesis. And of course, this allowed a lot of different products to be made, and a lot of engineering to be done in terms of how these different polymers could be shape-formed into useful things. So if we look today, polymeric products are ubiquitous. You would struggle to find a household pretty much anywhere on the planet, all across the nations, that didn't have something that was a product of the polymer processing industry in it. For example, polyester yarns make a very large amount of clothing that is used globally. And polyester in this case might be, say, a polyethylene terephthalate. If you go and look in your wardrobes, you'll find either fibre mixes or yarn mixes that are polycotton, polyester cotton blends, or another synthetic fibre. Nylon's sort of a little bit out of fashion these days because it's a bit clingy and a bit sweaty, but it's amazing how many different clothing products are synthesized or are woven from synthetic polymers. We can also look into the construction industry, for example, and thermal insulation. Many environmental standards these days require a minimum insulation specification, and you will find that one of the means that this can be fulfilled is through insulated board put between, say, a suspended ceiling and the outer skin of the ceiling. Some of these insulated boards would be, for example, expanded polystyrene, again, a product of the polymer processing industry. If one looks into geology and earthworks, you can find ground stabilization materials, typically meshes that are used to stabilize unstable ground in, for example, construction, or maybe materials that are as simple as temporary fencing around construction sites or roadworks. If you look at the sort of consumer products that you've got, you'll probably have a mobile phone. Many places on the planet, people have mobile phones. And it's amazing how that technology has been a step change in people's standards of living in certainly the poorer parts of the planet. And so if we look at the casings of mobile phones or the casings of just about anything, they're going to be injection molded polymers. They might be, for example, a high impact polystyrene, or they might be a polyethylene or a polypropylene. And so you'll find in these consumer products lots of examples of actually very smart polymer engineering. And so if we look today, there's a whole range of different uses that synthetic polymers are put to. And these different uses require different mechanical properties. And one of the things that we'll be exploring at length on this course is how the final mechanical properties of a product are as much about how the product is processed as it is about the polymer from which it's made. Because the way in which you process a polymer will affect the orientation of the polymer chains, which in turn will affect the tensile strength of the final material and the tensile strength in given directions. And so we can orientate polymers for stronger products in certain directions, or we can have unoriented polymers that give a different kind of strength. We can have polymers storing stress that when they're heated they contract, for example heat shrink sleeving. Equally, we might not want that to happen. For example, in yarns, if there's storage stress in yarn and we put it in a hot wash, your clothing will shrink. And so there's this intrinsic link between processing conditions and material properties that is really important to recognise right from the get-go. Now, polymer products, as I said, are ubiquitous, and that has brought with it a very great variety of engineering approaches. And so what we find is that the polymer processing machinery that's been invented to make these different products has applications elsewhere as well. And it's fascinating to say, look at the food industry to see that sort of crossover, because foods are made of proteins and carbohydrates, which are all actually biopolymers. And so we could say that a lot of food processing is polymer processing due to the molecular nature of the sorts of materials that are being processed. And so, for example, here on the whiteboard, I've put a diagram or a picture of a typical pet food product. It's actually a co-extrusion. And so you'd have two extruders, one extruding the red material, one extruding the white material, and a die that would allow those two materials to come together in a coaxial manner such that you shape form that product, which would then be chopped and then maybe cooked or fried as appropriate. It's not just pet food where you'll find extrusion technology, for example. Extrusion cooking and extrusion texturizing is a pivotal step in forming meat replacement products. And there on the board I've put two vegetable-based meat replacement products, typically soya-based. And the texture that is also important in order to give that product its final sort of chew is typically imparted by the way that it is processed. And the way that it is processed is using polymer processing-like technology. First thing in the morning, you're probably eating extruded products in terms of breakfast cereals. So if you look at the range of breakfast cereals that are on the market today, most of them will be produced by an extrusion operation. So for example, traditional cornflakes might be produced by corn on, not quite corn on a hot plate, but that's popcorn, but there will be a production process that involves a cooking type method. Or you could use extrusion cooking, shape forming in the die, and then chopping, and then either drying or baking as appropriate to form the final product. And then when you think of the variety of shapes that you get in breakfast cereal, for example, hoops or chocolate balls, then you can see that the sort of technology used to make polymeric products translates very well into the food processing industry as well. Now, the ubiquity of polymers has left us with a massive problem as well. And we can't look at polymer processing without looking at the long-lasting damaging legacy that the industry to date has brought about. And it's incredibly sobering when the extent of this damage is actually looked at. And it is this really that gives spur to innovating away from the way we currently do things. So we need to understand what we do today in order to understand why this damage has been caused. And then we need to figure out a way to stop doing it. And that may mean replacing the materials that we're using or processing things in a different way. But let me describe the sorts of things that I'm talking about. Not a day goes by when you don't hear about microplastic pollution. Now, microplastics are a very broad church. They can be, as I've pictured there on the board, and that is on a beach in Hawaii, and they're visible in this particular case. They're millimetre or multi-millimetre size lumps. Typically, it's mechanical abrasion of polymeric products, bottles thrown in the sea, for example, that cause this. The polymer chains that are synthesized are synthetic. There's no bacteria or fungi that can actually chemically break them down, and so they're just subject to mechanical attrition to produce smaller and smaller and smaller lumps of plastic product, which get everywhere in the ecosystem. And there are truly traumatic descriptions of how wildlife are dying as a result of ingesting multiple amounts or a lot of these microplastics. And so this is found globally. Seabirds in South Georgia, through to the southern oceans, through to the tropics, through to the northern hemisphere. Ingested microplastics in wildlife is a massive, massive issue. But microplastics go smaller than that. Microplastics can go down to, well, as the name suggests, the micron range. And their close cousin nanoplastics, when the attrition has been that much more, also exist. And so there's a growing body of evidence now how the small-scale microplastics and the nanoplastics are found in human tissue. And so they're being ingested through food and water, they're passing through all the membranes in the digestive tract, they're going into the bloodstream, and they're perfusing from there on into organs that have large blood supply. And there's been a number of studies that have revealed microplastics embedded in heart tissue, in intestinal tissue, and in reproductive tissue, both in humans and in animals. And we're only opening our eyes to this at the moment. A lot of these plastics might be, for example, PVC or polyethylene terephthalate. Polyethylene terephthalate is based on aromatic chemistry, and so the health impact in the future of these microplastics is unknown. They are unlikely to be inert. They may be endocrine disruptors. They may be causing mechanical damage in their own right. And so there's a huge and very legitimate concern now about what the legacy of microplastic pollution is going to be, both on the scale that I show on the board and on a physiological scale. Macroplastic pollution is also a huge, huge problem. I've put on the board there a picture of the Great Pacific Garbage Patch, which gobsmackingly is 3 times the area of France. And this is contained in one of the gyres, one of the big ocean currents in the Pacific Ocean. Now, there has been some work to try and clean this up, and it's heartening. It's going to take a long time because of the sheer scale of it, but it shouldn't be there in the first place. And so this comes around through basically bad and improper disposal of products, but also the ubiquity of these products being found everywhere. And you can imagine that the attrition of the plastics and of the UV on these plastics, this is one of the sources of microplastics as well. Microplastics and macroplastics in landfill is also a huge problem. Where do you put this stuff? These materials shouldn't be put into landfill. They should be recycling operated. And so there should be a closed loop economy that allows these materials to be reused rather than disposed of. And it's all very well saying should. Yes, of course, plastics recycling does exist, but it's not on the global scale that it needs to be at the moment to prevent any more disturbing legacies that these current disposal techniques are causing. So synthetic polymers are hugely problematic from an environmental and potentially from a health standpoint as well. And so what we need to do as the polymer processing engineers of the future is make sure that these problems are remedied, both in terms of addressing what we're currently doing, in terms of recycling and of reuse, but also in terms of how we develop the chemistry, how we develop the synthetic processes, how we develop the processing operations, how we even change the end use of products to ensure that we're not adding yet more environmental burden to an already damaging situation. So some of the current challenges that the polymer processing industry faces and the polymer engineers of the future will be addressing are listed here. This is an absolutely non-exhaustive list. These are things that I was pulling out of the air as I was writing this. So the first problem is persistency. We've talked about the Pacific gyres, about the Great Pacific Garbage Patch, about microplastics and how endemic they are on a global basis. And it's all down to persistence. So new materials going forward need to be non-persistent in the environment. This is hugely challenging because, of course, non-persistent materials can be made and synthesized, but we need to ensure that we've still got the ability to produce some of the products that are needed from the engineering materials that we've invented. And so there's this balance between having non-persistency versus the longevity in use of a product. And it may come up to the point where polymers aren't suitable anymore for certain applications. One of the things on a global basis that can try and be encouraged and uprated is effective recycling and effective reuse and effective upcycling. This is as much about politics as it is about engineering, and how this is implemented is very, very patchy on a global basis at the moment. And in many ways, it's a sticking plaster because it requires people to change their habits. And typically that can take a very long time and be subject to a great deal of backlash. And so the material innovation that would remove the need for recycling would maybe be a better way to do it. So what does that need? Well, it needs, first of all, the elimination of frivolous misuse of these products. we're seeing some progress in this. We're seeing, for example, Christmas crackers not having plastic gimmicks that are used once and chucked away. Single-use plastics are, certainly in some countries in the Western world, being reduced or eliminated. Plastic bags, for example, are also being incentivized against single use. It's a good first step, but is not necessarily the full steps that are required to address the environmental burden that we've got. So elimination of frivolous misuse will go some way. And of course, we need to understand what the impact assessment is in terms of a life cycle analysis of the materials that are out there at the moment. So we need knowledge. In order to replace engineering materials that we've got, we're going to need some very innovative chemistry and very innovative full-scale synthesis. With innovative chemistry, for example, some of the things that might be looked at is how you uncross-link materials, how you try and promote biodegradation, how maybe you can encourage existing bacteria, fungi, enzymes in nature to use polymeric products after a certain time as their source food, much as they would any other, say, carbohydrate or starch. And maybe changing the chemistry and the molecular structure of some of these polymers to closer resemble natural polymers may well be a good first step forward, so long as they can still have the engineering properties that are required for their end-use function. It's a very hard problem, but one that can be done. When we think about shape forming these new materials, the rheology of the materials are going to be probably very different to what's used at the moment. So part of this course is going to be educating you in what we do now, but also educating you in the fundamentals. For example, the fundamentals of rheology, the fundamentals of heat transfer, the fundamentals of mass transfer, so we can understand with a new material, firstly, how we characterize it, secondly, what that means in terms of processing, and thirdly, how we can then optimize processing conditions to take into account that increased level of viscoelasticity, for example, or the different heat transfer properties, for example, or the different shear thinning type characteristics. Of course, if we're shape forming, we also need to have knowledge around how these machines work, how we analyze these machines, how we design these machines, how we ensure that they are indeed fit for purpose with the polymeric products and hopefully the new polymeric products that we will be using to make the devices of the future. So as I said, this is far from an exhaustive list. These are just the things that cropped into my mind immediately. But the picture I want to paint is that there are many, many challenges going forward for the polymer processing industry, all of which needs addressing. And so that is my motivation for saying that the study of polymer processing is more important than it ever has been, such that we can transition to a set of technologies and a set of materials that remedy the environmental and societal and physiological damages that we've done so far.